In the last three videos, our attention has focused on the quantization of electromagnetic waves. We talked, in order, about blackbody radiation, the photoelectric effect, and the Compton effect. In this video, after we have seen how the radiative energy of a blackbody is quantized, we will discuss some aspects related to the Planck curve. We have seen how a blackbody is a theoretical object, but is very similar to many hot physical objects in nature. The black-body curve depends only on the temperature. As we mentioned in the first video, each wavelength on the x-axis represents a set of fundamental waves in this system. Each group is called a vibrating mode, and therefore each wavelength on the x-axis represents one mode. A single mode contains energy, and this energy is quantized and not continuous. In other words, each of these fundamental waves that make up a single mode corresponds to a single photon in Planck's hypothesis. Therefore, the number of photons in one mode determines the energy content of this mode, meaning its excitation. The Planck equation, especially this factor in the red box, determines how these photons are distributed among these modes. The distribution depends, of course, on the temperature. At a given temperature, some modes receive more photons than others. Modes that correspond to very short wavelengths, they hardly receive any photons. This is logical, since the temperature of the object is equivalent to the kinetic energy of its components, and this energy is not sufficient to excite these modes and emit photons that correspond to them.
But I wonder, at a given temperature, which mode or wavelength on the x-axis has the largest number of photons, that is, the one that emits the greatest radiant energy?
To answer this question, we may have to resort to some mathematics, specifically derivation. In calculus, if we have a function of some variable, and we differentiate this function with respect to this variable once, and set this derivative equal to 0, then by solving the resulting equation, we'll get the value of the variable at which the function assumes its maximum or minimum value. Here we have the Planck function that we saw in the first video. We will now differentiate this function with respect to the wavelength. After a bit of algebraic gymnastics, we will get the derivative. Now we will set this derivative equal to 0 and solve the equation for the wavelength. Eventually, we arrive at this result. It's called Wien's law. In fact, this law was known before Planck's equation, but no one knew in advance why it was true. Therefore, to calculate the wavelength that corresponds to the most active mode in a blackbody, we only have to substitute the temperature of this object into Wien's law. Likewise, in astrophysics, Wien's law is used in the opposite direction to determine the surface temperature of bright stars by studying the spectral distribution of their light.
All right, let's take the sun, for example. If we study the spectral distribution of the sunlight, we will see that the highest energy mode is that of the wavelength of about 500 nanometers. If we substitute this value into Wien's law, we will see that the surface temperature of the sun is 5,800 Kelvin, or 5,500 degrees Celsius, or 10,000 degrees Fahrenheit.
Let us now talk about another aspect of Planck's law. We know that wavelength is related to frequency by the famous relationship, where c is the speed of light. The question that arises is, can we express this Planck's law in terms of frequency instead of wavelength? The answer is yes, of course, but it's a bit more than simply substituting in for lambda in terms of f. In fact, we will have to take not all the radiant energy emitted by the blackbody, but only a sample of this energy located between two wavelengths, lambda 1 and lambda 2. Thus, we have an interval of delta lambda on the x-axis. While the height will be the function itself in this range, we can assume also that the lambda 2 is near to lambda 1, and the interval becomes infinitesimal d lambda. Therefore, the portion of energy that we will take is just the area of this shaded rectangle. It is equal to the width, d lambda, times the height, which is the function u itself. Thus we get the function relationship, where d here means part or differential. For the lambda itself, we can directly replace c by f. As for d lambda, we must differentiate the wavelength-frequency relation with respect to f. Here, what matters to us is only the magnitude, so we took the absolute value. Now we plug this into du equation. After some canceling, we get this relationship. And as we can see, this is Planck's law for energy density in terms of frequency. We have one question left. Is there Wien's law in terms of frequency just as there is Wien's law in terms of wavelength? The answer is yes. Deriving this law for the frequency f is also easy, but if we set the derivative equal to 0, the resulting equation is too difficult to solve by hand with respect to f. However, a good approximation can be made that makes the solution easier for us. Note that in this relationship, in contrast to the wavelength law, we have f cubed in the numerator. In the denominator, the exponential function, because f, frequency, is often large for light waves, will give, for most temperatures, values of the order of 1 and perhaps lower. Therefore, the large numerator will not be greatly affected by division by such a denominator, and for this reason, we can neglect the number 1 in the denominator. With that, if we now differentiate and set the derivative equal to 0, we will obtain a much easier equation to solve for f, and the result will be: this is Wien's law in terms of frequency and to a good approximation. Thanks for watching.